My name is Wayne Bussard, and we're here to discuss the Lakeshore Electric insulated case automatic transfer switch and its operation and maintenance. First of all, let's just talk about routine maintenance. When you have a unit like this at your facility, the unit should probably be tested once a week. A lot of people like to test it at nighttime. We have a plant exercise feature to automatically test the unit. A lot of times there's nobody there at night. There should be a way to verify that in fact it did start the engine, it did transfer to emergency, and it did come back. If you test it once a week, that's a good indication that if you have a problem, it will transfer to emergency for you. In addition to testing it once a week, there should be somebody that comes around at least once a week to look it over in general. You want to look it over and make sure no tow motors have run into it, no trucks have backed into it, and the display is operational. This display, 99% of the time, should say the normal power is available and the normal breaker is closed. In addition, the LCD display should start out with the word auto, meaning you're in the automatic mode. If you're in the automatic mode, the system is designed to home to the emergency source, and if the home to the normal source, and if the normal source ever fails, it will start the emergency source and transfer power to it. After the automatic, after the auto, you'll see one of three words, one of three options. It'll either say do not exercise, exercise with load, or exercise without load, depending upon how the plant exerciser was programmed. After that, the second line will have the date and the time, and they should be correct. Just noting those items indicates that the unit is still fully functional. After that, it's a good idea to open the door and just look inside. One thing you don't want to see inside is moisture. If there's moisture getting into this unit, condensation occurring anywhere inside, we need to check that out, call the local service organization, and find out how the moisture is getting inside our unit.
Dave, line 1, Dave.
The microprocessor controllers do not like moisture inside these enclosures. After that, you look around for any obvious signs of damage. It should be pretty clean and pretty dust-free inside of here. In addition to that, every couple years, and now we need to move to the back of the enclosure to look at the load bus. Every couple years, we should do a thermal scan on the main cables and buswork in the back of this equipment. When you do a thermal scan, you will have to remove the upper and lower covers on the back of the equipment. And you're looking to see if you have any hot spots on this bus. The hot spots indicate a trouble condition appearing, and it gives you time to correct the hot spots before you have an actual power outage or worse. When you do a thermal scan on this type of equipment, the utility cables are connected to these upper lugs. The load cables are connected to the middle lugs, and all the currents going in the upper lugs and out the middle lugs. So with utility power connected, the thermal scan is only going to show you the upper half of this equipment. In order to get a complete thermal scan, you need to start this unit, put it on generator power for about 2 hours to allow the heat to build up, and then do a thermal scan of the lower equipment, because that's when the current will be coming in these lower terminals and out the middle terminals. The next thing we want to talk about is fault conditions and manual operation of this piece of equipment. Even if you do all the necessary routine maintenance, there's a possibility that something will occur where your facility will go in the dark. It may happen for many reasons. The microprocessor could shut down on a fault mode. Fault modes for this microprocessor are controlled by inputs to the microprocessor such as ground fault, overcurrent, and a few other items. They're also controlled by the microprocessor trying to do something and that not happening. If the microprocessor sends a signal to close the emergency breaker, it needs to receive an input from the emergency breaker that in fact did close. If it doesn't receive that signal, it goes into a fault mode. When it goes into a fault mode, it shuts down and it energizes a trouble relay. The trouble relay, which is on the reader interface board, should be wired out to contacts to enunciate the fact that the transfer switch is shut down in a fault mode, and it needs operator intervention. Anytime this transfer switch shuts down in a fault mode, operator intervention will be required. Now, one of the common fault modes that you might see would be something like ground fault. If if we were sitting here in a normal operating condition, normal power is available and normal power and normal breakers closed, it's in automatic, but somebody was working on some equipment and accidentally touched some wires to create a large ground fault, this breaker could trip. And when it does, the breaker's open, the normal's breaker's open, so you're disconnected from utility power. The emergency breaker's open, so you're disconnected from emergency power. We're not trying to start the engine. Your facility's in the dark. If you come up to the display, you'll see, first of all, normal power is still available, but the breaker, the normal breaker is tripped. Also, it's indicating ground fault up here. It took the system out of automatic, and it's displaying fault. That's the first word, ground fault, or first word is fault, and then it says ground fault. It's always important if you get a fault to look at the next wording, because that tells us what the microprocessor's fault actually was. That's important for us to determine if it's a processor fault or a system fault. Once this happens, as an operator, you can say, we had a ground fault, somebody was working on a piece of equipment, we've cleared that problem, we want the system back on normal power. You don't have to call a service technician for that. If the system tripped off on something like ground fault, or the other one that you might see is fault bell alarm. Bell alarm is a contact that closes on an overcurrent condition. That can also be reset here. To reset it, you have to first move to the breaker. You'll see a light on the breaker. And to reset the light, we press the button next to it. That reset the light. In addition to that light, you'll see this red button that's popped out. That's the bell alarm reset button. You'll notice this breaker's not tripped. Its red button is still recessed, but this one's popped out. So to reset this fault condition, I have to press that button back in. Once I did that, this breaker's reset. Now, my microprocessor is still locked up on the fault condition. And in order to reset a fault condition on the microprocessor, I have to take it into the off reset mode. It was in the automatic mode, it is now in fault mode. To clear the fault mode, I have to put it in the off reset position, after which I can put it back into automatic. When I put it back into automatic, it will sense that normal power is available and reclose the normal breaker. So to do that, I press enter, which says select mode. I press enter again, which says off reset. I press enter again. I'm now in the off reset mode. Because of that, I've cleared my trip light and my ground fault light. Because I'm in off reset, I'm still not in automatic. Now that I've cleared the trouble condition, I have to go back to the automatic mode. I press enter, it says select mode. I press enter again, it says automatic. And when I press enter again, I put it in the automatic mode. It's timing the TDN 4, 3, 2, 1, and it's going to close the normal breaker. Now I'm back in normal. So that's a fault condition that could occur due to an overcurrent or a ground fault that a normal operator could come out and reset without having to call a service technician. Now, if the fault is more than a ground fault, if it's normal failed to close, emergency failed to close, normal failed to open, emergency failed to open, or some other unknown fault condition, when you come out here as the operator, you want to take manual control of the system. And to do that, to take manual control of the system, we want to shut off our automatic controls. Our automatic controls are basically everything you see on this side of the switch. In order to shut off all of our automatic controls, we take this maintenance disconnect switch, which is in the normal position, and we'll move it to the open position. Now it's in the open position, and our microprocessor is not going to try to open or close either one of these breakers. Because of that, I now have two manually operated breakers. The top breaker is typically the normal breaker, but whichever one says normal is the one that connects your facility to the utility. The one that says emergency is the one that connects your facility to the generator. So if you were in a position where you had no power to your facility because this breaker was open and this breaker was open, the engines weren't running, the controls weren't doing what you needed them to do, you could open the maintenance disconnect switch and come out here and manually either close it to normal or start the engine generator set and then close it to emergency. The way you do that with any stored energy breaker is by using, you have an open and close push button and a charging handle. There is an indicator here to indicate whether it's discharged or charged, and an indicator to indicate whether it's opened or closed. If I want to close the normal breaker, I charge it up, then I can, once I do that, because I've disconnected all my control power, I can open it, and that's all I get out of it until I recharge it. You pull the handle until it swings free. That means the breaker's charged, and it's indicated that it's charged. Once it's charged, I can close it and open it again. So if I want to close normal, I press that button, my normal's breaker is closed, and if I have utility power, I've supplied that to my facility, and I'm back up and running, even though my automatic controls need to be looked at by a service technician. You never want to close the normal breaker and the emergency breaker at the same time. It's one or the other. You don't want the utility to backfeed the generator. You don't want the generator to backfeed the utility, so you only want to close one or the other. If I want to transfer to emergency, I first have to open the normal breaker and then close the emergency breaker. Now I'm on the emergency side. To keep you from accidentally closing these two breakers, we arrange a mechanical interlock, which are these two metal rods on this side of the switch. Because we have these two rods here, if I were to try to close this breaker, it would not let me. And if you come up here and say, wow, the normal breaker won't close, you got to be sure that, in fact, your emergency breaker is open. Also, and discharged. Now, so that is effectively how you can manually operate this transfer switch and put it in either the normal or emergency position if the situation comes about that you need to do that. Now we're going to talk about the automatic controls that allow this system to transfer back and forth, what they are and how they work. First of all, this is a 480 volt system, and our control logic works at 120 volts or 24 volts or 12 volts on the DC side. To get the 120 volts, we have two control transformers up here. One's called the ECT for emergency control transformer, and one's called the NCT for normal control transformer. The ECT steps 480 volts of the generator voltage down to 120 volts to charge the electrical motor in the emergency circuit breaker and also close this circuit breaker. The NCT, or normal control transformer, steps the normal utility voltage down to 120 volts to charge the normal circuit breaker and or close the normal circuit breaker. After that, we have a voltage sensing relay over here. This is a Lakeshore 3-phase voltage sensing relay. It is set up to pick up when all three phases attain 90% voltage and drop out when any one phase falls below 80% voltage. It has a set of contacts on top of it, and it also has a LED to indicate it's energized. A quick way of knowing whether you have utility voltage present or not is when you look in here, if utility voltage is present, that LED will be on. It's presently on because we have it hooked up and working as a 480 volt system right now. The contact on this will go to our microprocessor to tell us whether or not we have utility voltage. If we have utility voltage, the microprocessor will tell this system, if it's in the automatic mode, to home back to the normal source. Next to the voltage sensing relay, we have a frequency voltage relay, an FVR. That's a single-phase relay that senses voltage and frequency of the generator. When the generator gets up to 90% voltage and frequency, there's an LED here that will come on. When that comes on, the contacts of this FVR will close, and that will tell the microprocessor we have generator voltage available. As far as the controls for the operator, we have a control panel here. The first thing to note is a maintenance disconnect switch. Anytime you need to maintain this switch, or when you need to take manual operation of this switch, you need to turn the maintenance disconnect switch to open. When you turn it to open, we kill all DC voltage coming in and AC voltage coming in. You'll notice when I turned it to open, the voltage sensing relay dropped out because the switch doesn't even know utility power is available at this point. EFR doesn't. Normally, this switch should be in the normal position. It will not transfer automatically unless it is. The next switch we have here is the keypad enable button. Right now it's in the enable position, and I can operate the microprocessor from the keypad. If I want to disable it, I move it to the disable position, And then I can close and lock this door. If anybody comes by and tries to operate my transfer switch, it would say keypad disabled. So the purpose of that is to prevent anybody from operating this transfer switch, especially if it's an outdoor unit. If they're driving by and they can hit the keypad. For our purposes, we're going to leave it enabled. The next button here is called load test. We set our switches up to be a cycle load test. If you push and hold this button for 2 seconds, the microprocessor will show load test underway. It will go through its standard time delays, transfer to emergency, and transfer back to normal. The standard time delays, once you push this button, are going to be first, it's going to go time delay, engine start. It's factory set at 3 seconds, and after a 3-second delay, we're going to send a signal to start the engine. That would come off of these terminals down in this corner, and this is our engine start signal. Once we tell the engine to start, we're waiting to attain engine voltage, and we'll know that by this frequency voltage relay. When this picks up, we're going to start our next time delay, TDE, time delay to emergency, which factory defaults at 3 seconds. When the time delay to emergency times out, it's time to begin our transfer to emergency. So at that point, we will open the normal breaker. So we will send a signal, and this breaker will open. Once this breaker opens, we start our time delay to neutral, TDN. Again, factory set at 3 seconds. Upon completion of the TDN, we will send a signal to close the emergency breaker. Once the emergency breaker is closed, you're on emergency power. Because it's a cycle load test, as soon as we are on emergency power, we start the next time delay, which is time delay to return, TDR. That's factory set at 12 minutes. When the 12-minute timer times out, the unit will begin its transfer back to normal. The way it does that is, it first trips the emergency breaker, it opens the emergency breaker, it starts the TDN, time delay neutral, which is the dead bus time to allow motors and everything in your plant or facility to wind down before we connect it to a different source. So the TDN will time out, factory set at 3 seconds, and afterwards it will close the normal breaker. You're now back on normal power. At that point, we start the TDEC, time delay engine cooldown, factory set at 10 minutes. When the time delay engine cooldown times out, we open our engine start contacts and the engine shuts off. There is also another timer called MRT, minimum run timer. So long as we've satisfied the minimum run timer and the time delay engine cooldown, that's when we will send a signal to stop the engine. The other button we have here is override TDR. The reason we put an override TDR contact in here is if you're doing a load test, the 3-second timers aren't bad, but the 12-minute time delay to return, a lot of times you don't want to wait for. So when you see the time delay to return timing out, a lot of times people will want to reach in here and say, override TDR, and the transfer switch will begin to transfer back to normal at that point in time. Additionally, after that, we have a power supply board here. And on that power supply board, you need to bring battery power into the left-hand side of it. That's what these wires are here, battery power. That can be 12 or 24 volts DC. And what we do here is we regulate the output to 9 volts for our microprocessor. We also take the output down to our relay interface board. Now the relay interface board has to have the proper relays in it, either 12 or 24. Although the power supply will work on 12 or 24, the relay interface board has to have relays in it that match the battery voltage, either 12 or 24. What we do with the relay interface board is we provide dry contacts to indicate several items. Number one, do we have a fault condition? Anytime we have a fault condition, we activate a trouble relay to enunciate to somebody that this switch needs operator intervention. We also have contacts to indicate system in normal, system in emergency, normal power available, emergency power available. They're brought out to dry contacts. There's a lot of people that have various types of SCADA systems, but one of the things that interfaces to pretty much anybody's SCADA system would be a dry contact. So these dry contacts can be wired out to your SCADA system, to lights, or to horns, or to whatever you want to not see. After that, we have the main control board, which is up here on the door. We're going to talk about the LCD display and how to program the microprocessor. If you were to hit enter, it'll say select mode. And if you hit enter again, it will tell you what mode you're in this case, automatic. As I scroll down, I can go to hand crank, which means start the engine, but don't transfer to emergency. I can go to load test, which means start the engine and transfer to emergency. And I can go to off reset. So the modes of operation are automatic, hand crank, load test, and off reset. The fifth mode, which you can't get to or control, is what we call fault mode. Anytime we have a problem, we go into a fault, it will show up on here, and that's really a mode of operation that you cannot select from the selector switch. So, right now, we are in automatic. The next selection, and I should also mention that the first word here is auto, because you're in the automatic mode. The next description really is a description of if the plan exerciser is set up or how it's set up. The next thing that we're going to talk about in addition to the mode is set current time and date. If you were to hit enter here, it's going to ask for auto daylight savings time. Auto daylight savings time changes. You can select yes or no depending upon what area of the country you're in. Also, we have microprocessor chips in this microprocessor that we burn with versions of our firmware. Version 166 and newer has a correction for the daylight savings time change that the government put into effect a year or two ago. If you have a version prior to 166, it will still do the daylight savings time, but it will do the daylight savings time change in accordance with the old rules, not the new rules. So the first question it asks you under set time and date is auto DST change. That's daylight savings time. We have this for yes. That's what our default is. If you hit enter, it will show you the time and military time, the day, and the date. If you want to change any of these, every time you press enter, the cursor will move under one of the digits. When you get under that digit, if you want to increase it, you press the up arrow. If you want to decrease it, you press the down arrow. You can scroll through each parameter you're allowed to change in the time and the date, and when you get done, it will take you back to the main menu. So that was set current time and date. The next one is set up timers. I've already reviewed the timers, but we can go through them again fairly quickly. If I say set up timers, the first one is TDES, time delay engine start. That's the time delay between the time the utility fails and we send a signal to start the engine. I have this one set for 6 seconds. The next one is TDE, time delay to emergency. That's the time delay to allow the engine to warm up and stabilize in frequency and voltage before we begin the transfer from utility to the engine, and it gives the engine a time to stabilize. On this one I have it set for 6 seconds also. The next one is TDN, that's time delay neutral. That time delay is in effect from the moment we open the normal breaker until we close the emergency breaker on transfer to emergency, and it's in effect from the moment we open the emergency breaker until the time we close the normal breaker for transfer back to normal. The next timer we have is TDR, time delay to return. That's a time delay that is there to allow the utility to stabilize before we arbitrarily transfer back to it. A lot of times when utility power comes back, it comes back momentarily and fails again. So we want to be sure utility power is back before we take everything off this engine, put it back to utility power. So we wait for a TDR, time delay to return. That's set typically at 12 minutes. Then we have TDEC, time delay engine cool down, which we have set for 10 minutes. And that's the time that after we transfer back to normal, we continue to run the engine to allow it to cool down before we shut it off. In addition to time delay engine cool down, we have an MRT, minimum run timer. Both of those that's also set for 10 minutes, and both of those have to be satisfied before we remove the engine start signal. Now, after setup timers is setup plan exercise. There's a yes and a no. Right now there's a yes after. The cursor is under the yes. If I move it up, it'll say no. This is how you select load or no load. Presently, we're in a load situation for the plan exercise. And then I have a start time. Again, it's military time. Let me know what time you want to start. I put in whatever time you want this unit to start, and then we press enter. That takes us to the next screen, which is a duration. We know what time you're going to start. Now, how long do you want to run? This is in hours and minutes. The cursor is under the hours right now, and we can tell it to run for 1 hour, 2 hour, however long you want it to operate in hours and minutes. And when the duration time is done, it will shut down. The next screen takes us to the days that you want it to work. And it says caps equals on. All the days right now are in lowercase, meaning it's not going to exercise on any of these days. If you want it to exercise on these days, you have to change that to an uppercase. The cursor is underneath this letter. If I hit the up arrow, that goes to a capital. So now it will start on a Sunday. You select whatever days you want it to operate, and when you press enter, it will take you to the next screen, which, after plan exerciser, we have restore factory defaults. If you set the timers up to allow for a test that you're going to do, you may move them down considerably from their recommended values. And if you want to get them back to their recommended values, you can simply go to here, hit enter, and it will restore factory default time settings to the microprocessor. After restore factory default, there's an LED test screen. If I hit enter, it'll tell me to press the up and down arrows together, and that tests all the LEDs to make sure they're functional. Finally, there's an about screen. When I hit the about screen, it tells me what firmware version I have and what my configuration is. These are important for us to know if we're trying to troubleshoot this over the phone. I need to know what configuration you have and what firmware version you have. I can look up on the drawings what your configuration is, but to verify it, it's good to go to this screen and read it right off the microprocessor. And those are all the parameters you can set from this keypad. To give you a look at how this operates automatically, we're going to go through an actual load test. It is presently hooked up to a 480 volt source on the normal side, and normal power is available. It is set to start the emergency source when it signals it to, and that'll put power on the emergency side to allow it to effectively transfer to emergency. And because we're doing a cycle load test, the TDR will then time out, and it will transfer back to normal. So to see the sequence of events, to do a cycle load test, we press the load test push button for 2 seconds, 1001, 1002. You will see the display says, load test cycle underway, 3, 2, 1. Now, it's waiting for the emergency to warm up, 3, 2, 1. It's going to open the normal breaker, time delay to neutral, 4, 3, 2, 1. It's going to close the emergency breaker. We're now on emergency power, and although you heard the noises, the normal breaker is open, the emergency breaker is closed. Because it's a cycle load test, as soon as the emergency breaker closed, it began the TDR. So right now it says awaiting TDR, 11.7 minutes. When that times out, it will begin its transfer to normal. The transfer to normal begins by opening the emergency source. So that we don't have to wait the 11 minutes, I'm going to use the override TDR button here, and when I press that, you'll see this breaker will open. 6 seconds later, this breaker will close. So I'm going to press that now. He opened. We're going through time delay to neutral. You're going to see the normal breaker close. Now we're back on normal power, and we started our cool down time. So now we have time delay engine cool down, and it's 1.8 minutes. I set it for 2 minutes. And after 2 minutes, it will open its engine start contacts, which will turn off my emergency source available LED. We have 12 seconds left to go on the time delay engine cool down. We're down to 6 seconds. And when that 6 seconds expires, this will go, it turned off emergency and it went back to reading the time and the date. And that was a cycle load test, a demonstration of cycle load test. Anytime a timer is in effect, it will be displayed on the LCD and it will count down. When it reaches 0, whatever's supposed to happen at the end of that time delay, that's when it will happen. That was a demonstration of the load test switch using the load test push button in here. I might also mention that this is a load test cycle, so it only momentarily tells you that utility power failed. Now, we also have, as we were talking about the modes, and I don't think I mentioned this there, if I go in here to select mode, and I take it to hand crank and I hit enter. Okay, I lied. Can I start that over?
Sure.
Okay. What I forgot to mention here is that was a cycle load test using the switch on the inside. If I want to do a load test by selecting the mode, I go to load test, I hit enter. It's going to start the engine, wait for it to warm up, and then it's going to complete a transfer to emergency. Now, because I put it in load test, I told the microprocessor you don't have normal power. So if I'm sitting here in emergency and the mode was selected from the keypad as load test, and the emergency source fails, it doesn't go back to normal. Now, if I fail the emergency source right here, okay, it says I'm in mode load test. The emergency breaker is still closed, but it's not available. It can't start a transfer back to normal because, as far as the microprocessor is concerned, when I'm in load test, it doesn't have normal. So a point about putting it in load test, it's there for maintenance, but you can't just send it to emergency by putting it in load test, figuring that if the generator ever fails, it's going to go back to normal. It's not. If I wanted this to go back to normal now, I would go back to the automatic mode. The automatic mode knows emergency is not available, normal is, so it opens the emergency breaker, goes through the TDN, and closes normal. And we're back under normal power. Okay, if something doesn't work on this automatic transfer switch, and you have to get a service personnel out here to troubleshoot it, there's really 8 steps that I look for to begin with. Number 1, did battery voltage get connected? Okay. This microprocessor runs off of battery voltage, and we need battery voltage to be connected. Not only do we need it to be connected, it has to be the proper voltage for the way we designed it. There's a nameplate on the door that indicates what voltage, DC voltage, this is designed for. And that's the voltage that these ice cube relays are. All right. The microprocessor itself runs off the 9-volt output of this power supply. And the power supply can take 12 or 24 volts. But there's a direct pass-through of this battery voltage to these relays to allow them to energize. If you have 12-volt relays and you plug 24 volts in here, when the microprocessor tries to energize these 12-volt relays, it pulls way too much current and can overheat outputs of this microprocessor. If you put 24-volt relays in here and you only have a 12-volt battery, when the microprocessor tries to pick up the relays, it can't because it's only putting 12 volts across a 24-volt relay and it won't energize. So it's important to look at, did you connect battery voltage? Is the battery voltage a proper voltage that the unit was shipped with? And are the relays of that same voltage? The next thing is this maintenance disconnect switch in the normal position? Did somebody take manual control of this, put the maintenance disconnect switch in the open position, do a few things, walk away from the unit, forgetting to turn the maintenance disconnect switch back on? Are these relays in the proper position? Every job that goes out of here has a set of drawings with it, and on the set of drawings it tells you what relays are to be populated and what relays are not to be populated. We've had situations where people have been working in here and a relay falls out. Maybe they don't know where it goes, but they pick it up and they stick it in one of these sockets where it's not meant to be. And then the microprocessor cannot do its job. For instance, these bottom 4 relays have to be open normal, close normal, open emergency, close emergency. If you pull out open normal and stick it up in the wrong socket, the microprocessor cannot signal the normal circuit open from that point on. So we need to verify that you have the proper relays in the proper sockets as shown on the drawing for this switch. Another troubleshooting scenario is something went wrong and somebody changed out the main control board. These main control boards are configured for the options and accessories that this switch was built with. You need to verify that the configuration of this main control board matches the design of this switch. If, for instance, if this is configured for closed transition transfer, but the switch was never set up for closed transition transfer and in fact has a mechanical interlock on it, it's not going to work. So we need to verify if you changed out the board that the configuration of that board is proper. And the other issue is if you did change out the board or anything else, we have a ribbon cable here. It connects from the bottom of the relay interface board to the side of the microprocessor. It has a red stripe on it. The red stripe has to line up with a red arrow on the microprocessor, which is on the top side. And down here, the red arrow has to line up to the, let's say, relay power terminal, or a little red arrow on this board. If that is reversed, let's say bad things happen. And then, of course, the other thing I tend to look for, I take this cover off. There's 6 screws that pull this cover off, and that allows you to look at the main control board. And you want to look at the main control board for obvious signs of any damage. Does anything look like it overheated? Does anything look burnt or anything like that? And those are the first 8 steps of troubleshooting. To go a little bit further into the troubleshooting arena, when we're sitting here with normal power on and the normal breaker closed, there are, on this side, and I know you can't see them from there, but on this side of the microprocessor, there are diagnostic LEDs. Let me see if I can find a control board. Let's take a bit of a break. Okay, to continue with the troubleshooting techniques, we have a unit that's outside of its case here. And if you were to pull the cover off the back of the unit we were just looking at, this is what you would see. And obviously you look for any signs of burns or damage to this microprocessor board. The microprocessor board plugs into an LED board and an LCD screen and a keypad. And this is pretty much what it really looks like behind that door. To do some additional diagnostic testing, you look at the diagnostic LEDs here. The ones on the top are inputs. The ones on the bottom are outputs. I have a listing of these LEDs and a long description of which we'll put on a PDF that will be on this video. But there's also a nomenclature right next to them. And the ones that you're going to see, the inputs you're going to see here that are on are NOR for normal power available, NAX for normal breaker closed, and MSE for menu switch enabled. Now, one way to see if this board is getting the responses it should as far as inputs go is to go to the menu switch enable and turn it on and off. And as you do that, you'll see this third LED turn on and off. Also, because you know you have normal power, and you know the normal breaker's closed, NOR and NAX should also be lit. If those are lit, that's saying the input is getting to the microprocessor. If the microprocessor is alive and has a heartbeat, it's going to turn on an output. Matter of fact, the 2 outputs it's going to turn on are normal breaker closed and normal power available. That's in direct reference to seeing these inputs. And that tells you the microprocessor is working. In addition to saying normal breaker closed and normal power available, there are going to be some output LEDs on. The output LEDs are going to say system in normal and normal power available. And these diagnostic LEDs help determine if you have a wiring issue to the microprocessor or if the microprocessor's not doing its job by receiving the inputs and lighting the appropriate outputs. That would be the 3rd step, or 9th step of troubleshooting.